All right. So in the previous lecture, we did started our topic of support vector regression, and in support vector regression, the concept says that we do have epsilon tube instead of hyperplane, and as what I have explained related to this epsilon tube is the data points which are coming inside the epsilon tube are the valid points and which are coming outside the epsilon.
Hi, sir. Sorry, I was just away for a minute.
Yes, I'm audible. Yes, can you hear me? Okay, so yeah, so anything coming outside the epsilon tube was considered as error point. Okay, then it comes to the width of the epsilon tube, which we were taking as 2 epsilon. Epsilon is something that we are calling as a parameter, and this parameter is just like as margin, as we have seen in the hyperplane. Here also we want to increase the width of the epsilon tube, which is like 2 into epsilon. Epsilon we are taking from the regression line till the boundary of your tube. Okay, so that's what been considered here, and other terms are slack variables. The points which are above the epsilon tube are said to be slack variables. Below the epsilon tube are also called as slack variables. They are represented as slack and slacks star. This is for above and this is for below the epsilon tube, just to differentiate. Okay, something which is above, as we have seen in the hyperplane, that it is positive region, this is negative region. Here we don't have any positive negative region because we are dealing with the regression, so that's not the point. But okay, still they are differentiating these points. And these slack variables only, I think that these are support vectors only, because in consideration to the support vectors, we are getting the width of the epsilon tube. If it happens that your slack variables are identified, then understood that till here, okay, your epsilon tube is present. That's what we have seen in the representation also. Here you can see. Okay, so the distance of these points are being considered from the epsilon tube. You can see here epsilon tube and the distance of the points which are present outside. They are represented as slack. And we can also mark them as the vectors. Okay, like this. Okay. We have studied fundamental points related to it yesterday. So epsilon tube, think of it as margin of error. Okay, because epsilon tube is like in classification margin. Here is everything is your epsilon tube. We are allowing our model to have those points and not to care about any error inside. That's what I do. Nothing inside tube, no error. Outside the tube, there is an error. Okay. So any discrepancy between any like distance between the point and the regression line or the hyperplane, we don't care about the area where it falls. For the points that lies outside, there is an issue. The rest I don't care. They are epsilon insensitive. Okay, this tube is epsilon insensitive tube, and any point coming outside it, we will consider them, and we have to take care by measuring the distance of that point from the tube itself. Okay, not from the regression line. Okay, we are not considering the distance from the regression line. This is your regression line, this dotted regression line. Okay, so the distance of the points which are lying outside will be considered from this tube, because everything inside is fair, rest which is outside is unfair. So we are taking the distance from that. And the formula is like, okay, 1 by 2 w square, the same thing, the same objective function we have seen in the classification. This is the objective function. That is the width of the hyperplane in classification, and here it is the width of your epsilon tube. Okay, so I think their consideration will be same. They want to maximize the width. That's what they want to do. And what is width? Width is 2 epsilon. Okay, so it will be like w square by 2. That's what they are saying. Okay, and the conditions, constraints. What will be the constraints? The constraints will be related to slack variables only, because they are judgmental here. Previously, in case of hyperplane, the judgment was taken according to the support vectors only, but they were the data points which are present on the class boundaries. Similarly, here we don't have any class boundary, nothing like that, but we are having the data points which are present outside the tube. So, how many data points can be present outside the tube? That is the question. We have to put them in the constraint. This should have to be minimum. It's saying that this should have to be minimum because this is error. Understand, this is error. I want, okay, let's see, this should have to be minimum. Okay, so it's error, and we believe that error should not be more. You want to increase the width, okay, for increase in the width it is 2 epsilon. Okay, what should be the value of epsilon? Don't know. We'll try for that. That's what the algorithm do. We're not going to study a separate maths for this algorithm. No, the maths which we have studied, that was like we did for the classification. That's it. No separate maths. No other maths for it. Okay. Then support vector. The point lie outside are dictating what the tube would look like. I was already telling you this thing. They are responsible for the tube. So these point outside the tube are called a support vector. Okay, so the ones which you are saying as slack star, they are support vectors. They will help me in making the epsilon tube. Okay, that is the formulation of epsilon tube. Now you can mark. I've already marked in the previous diagram. Now you can see here clearly. Okay, so this method is called as support vector regression because effectively all the points can be represented as a vector in the 2D space or multi-dimensional space. We can represent everything in the vector format. The data points can be represented accordingly. Okay, so that's for linear support vector regression. What will happen for non-linear regression? See, in non-linear regression, the data is not separable by using straight line or regression line. Okay, just like think polynomial regression. Polynomial regression, there also we are saying that the points are not fitting over a line, the points are fitting over a polynomial. Okay, got it. So Here too, we have to follow the same approach. So to solve this problem, we have to use higher dimensional space, and then we have to make them linearly separable. See, you have to apply some trick to separate it. Okay, without that, it's not possible. Okay, so what trick you are going to apply? We'll increase the dimension space from 2D to 3D. I've already told you we have to perform the transition. And we want the data points to be clearly visible. And then we can apply the technique, what we are expecting. How this thing goes? Well, let me share my entire screen for this particular concept, and then we will understand how you are going to perform this in regression. See, in classification, the data points, if they are present, depends. What is the distribution? If you are having the data points like this, that means you are having a positive class and the negative class, and the negative class is inside the positive class. Obviously, it is non-linearly separable. Then what you did, you created one more axis, and you can project this negative points over this axis. Then, because it is 3D, so you can classify it with a hyperplane. But here, but here, you will ask, sir, we are now studying regression, sir. So in regression, why this thing has been there, sir? Why should we apply? Okay, now the point is, okay, they have to refer the approach, the concept accordingly, because my algorithm is still SVM. So it will follow the rule for SVM. Okay, when you are having 2D, then they told we can make a regression line. But when you are not having 2D, when you are having high dimensional, okay, more than the 2D. So they are saying that non-linear, we can't represent data on linear scale. That means that means the relationship between x1 and x2 is not linear in nature. Okay, that means the features are having the target and the variable. Okay, let's consider that thing is having non-linear relationship. Then what can be done? This issue we have already seen in linear regression, and there we have used polynomial regression. Okay, just we have converted the features into poly, and again we have used a linear regression only. The equation which we have used is like linear regression only. You have written like this: y equal to beta naught plus beta 1 x square plus beta 1 x, and then next you have used this thing. Okay, next you have used like beta naught plus beta 1 x plus beta 2 x square and so on. So such kind of equation we have seen in linear regression, that is termed to be as polynomial equation. However, the arrangement which we have done is like linear only. Okay, only the thing is it just named as poly because of higher degree of x of the features. Similarly, here they are saying the same thing. What will happen if the relationship between target and the feature is not linear? That means the data points will be like anything, like they can be like anything. So what should I do here? If the distribution of data set is not being represented by a regression line, then we require a polynomial. For a polynomial, sir, what is the setup? What is the setup for polynomial? For polynomial, again you have to do that thing. You have to, okay, here here we have to make epsilon tube. Here we have to make an epsilon tube for the regression, but they are referring the concept for non-linear in this way. That means if this is a 2D representation where the classes are present in this way, non-linearly separable, then they are providing a mapping function that is called as a kernel. Kernel is a mapping function, and that will project this 2D on 3D. Then you can separate the data points. That's what you can do. Okay, and I guess instead of making this plane, we'll be making a tube. I think that is much more better. Make a tube. Okay, and again, one more question will arise, sir. Regression, we are having plus point, plus red and green. What does it matter, sir? ये तो matter is not been like regression. In case of regression, what is this two class, sir? We are not been in that particular consideration. But at least the relationship between now understand technically. I agree with you that you will say, sir, we are unable to understand why they did. Okay, we are unable to understand because you are here showing red and the green points. Title which you are showing is non-linear support vector regression. So, sir, it means, sir, two class, sir. Here you are showing two class, and I can entirely relate this diagram with classification, sir. So it's not the case of regression, sir. Yeah, I agree because here you are making hyperplane. It's not a case of regression. Obviously, it's a case of classification only. But how I can relate this thing? I can relate this thing in terms of, okay, regression only. When you are having non-linear relationship, they should have to say this statement: non-linear relationship between y and x, between the feature and the target. Okay, and obviously we are having so many features. Let us suppose this is y, this is x1, this is x2, this is x3. We are having so many features and everything is perpendicular to each other. Then what you are going to do? Obviously, this is ND data. Okay, four dimensional right now. This is 4D data. And the data points are present like this. You have to make an epsilon tube. Obviously, epsilon tube you have to make. Okay. Now, making epsilon tube, where whether there will be a regression line here, that's a question. They haven't cleared the point. They haven't cleared the point whether there is a regression line here. I don't think so there will be a regression line in this tube. There will be, okay, 4D data na, there will be a 3D plane instead of regression line. There will be a 3D plane instead of regression line. Understand this thing. And obviously, I think that will be inside the epsilon tube. That 3D plane, that 3D will be inside the epsilon tube. Okay. Because you are having 4D data, so hyperplane will be of 3D, like this. Okay, but I don't want to say it's a hyperplane. No, no, sir, it's not a hyperplane. Don't say it hyperplane. Okay. So let me put this thing into epsilon tube. So anything which is coming inside this tube, any distribution is fair point. Anything which is coming outside is unfair point. So in this particular case, when the relationship is not linear, okay, when your data is not linear, that's what I am thinking. That's what I am thinking. Because in regression, we are having linear regression and non-linear regression. Linear, okay, you say y equal to mx plus c. With a line, you can separate. Okay, that's what you can do. And sir, and what's the equation? That's what you say. Y equal to beta naught plus beta 1 x plus. That means every feature is linearly related with y. But what will happen if it is not linearly related? Then it is a polynomial. Then if it is polynomial, then how I'm going to put it into my consideration for the relationship between y? Okay, higher order. Okay, fine. So that's the concept which they are mentioning here. Okay, and we do have many kernels. Okay, and like Gaussian RBF kernel, polynomial kernel, sigmoid kernel, we are having many kernels. Okay, by default, that is RBF. By default. Okay, that is radial basis function. Okay, so we can assume kernel as a similarity function which implicitly maps the data to infinite dimension plane. Here, mapping has been done. Here, we have to map the data in kernel. If data is present in this way, in 2D, convert it into 3D in this way. This is RBF. That is Gaussian RBF. Gaussian you very well know. E की power minus x minus nu का square upon 2 sigma square. 1 upon square root of 2 pi. Okay, so that's Gaussian. We are having other kernels also. Okay, like sigmoid, and I will tell about them. There are various other kernels which you have read about, and they do have some formula. Okay, so again, if I get to the point here, which we have to understand thoroughly, SVM, it has been said, it has been said, you can perform classification, you can perform regression. In classification, you are having hyperplane. Both we are taking right now basic case, linear. Here also linear, here also linear, we are taking basic case. There is no hyperplane, here is the epsilon tube. Now the question arises, sir, if we are not having linearly separable data. So separability, sir, comes under sir classification, sir. Separability comes under there, not here. Okay, separability comes under classification. Regression, there is no separability. Okay, but still, what internal you have understood that I am having two types of points. One are good points, one are bad points. Good points are points which are inside the tube. Bad points are points which are outside the tube. Here in hyperplane, in classification, there is no good and the bad. Only we are having class A and class B. That's what we are having. And if I let you know one more thing, in classification also, if you are having such kind of diagram, any point which is coming here, any point which is coming here, okay, you are saying this is B and A, any point which are coming here, they are, these are support vectors, not these are not support vector in classification. So what they are, if I say what these points, like whether they are, these are B points or whether these are A points, they can be A, they can be B also, they can be mixed A and B. I told that we are going to make some soft margin. Okay, we are looking forward for hard, but hard can give overfitting. So some misclassifications or some mistakes I can afford here. I can try to increase the width max. That's what I can do. So if you consider this diagram of classification, where you are having some points inside the hyperplane also. Okay, inside the hyperplane also you are getting some points. And if I turn this thing into regression, then anything which is inside is good and anything which is outside is bad. So these are slack variable, they are support vectors. In terms of regression, they are error points, they are errors. Okay, same diagram I can turn, same diagram understanding I can turn. What can I do? And instead of this hyperplane I can say this is epsilon tube. Same diagram, I haven't changed anything, just terminology changed, understanding thought changed, the interpretation of data points changed. So what's the issue if it is saying that because this is 2D and linearly separable, what will happen if again I am having 2D non-linearly separable? Non-linearly separable, I am having the points which are continuous in nature. Then what can I do? So the concept of classification is not applied. Regression is applied. We have to show the distribution under epsilon tube. So same data points, they are present. Okay, this is regression line, epsilon tube. Same. But if we are in trouble where this y and x are not related by a line, then what to do? That's what they have explained. Use kernel trick. Whether you are dealing with a classification problem, whether you are dealing with a regression problem, use kernel trick. Because they are saying that if you can't relate the data points which are in polynomial by a regression line, then you have to do something, and you have to apply a trick, just like we did here. We did here. Okay, by applying a trick. RBF, Gaussian kernel we have applied. So these points are projected over the surface, and this will be the decision surface. So here I will say, in terms of regression, what I will say, data points are distributed like this. Okay, I will take the data points from 2D to 3D. Okay, don't consider classifier. In case of regression, don't consider classifier. You say that okay, data points are just projected on 3D. Okay, and for 3D, will be no line, there will no regression line, there will be a plane, regression plane. That's what we can say, regression plane. However, in terms of classification, the things are very much clear. But in terms of regression, we have to assume that what's happening. And therefore, I have made some few more notes related to SUM kernels, especially only for kernels. This is linearly separable. We are studying from the day one only. This is non-linearly separable. Okay, so support vector machine are popular, powerful algorithms which can perform both the tasks. But how? That's what we have seen. Okay, so if this is 2D, with the help of kernel, you can represent 2D on 3D, and you can separate, you can classify. That's what kernel do. And transforming a data from lower dimension to higher dimension, that is called as kernel trick. And this trick obviously requires a formula. And that formula, just you have seen one of the trick, that is Gaussian RBF. And this is your e key power minus, this is the formula for the Gaussian. You put the points, they will be located here. These points will be located here. If you put the points into this formula, okay, the distribution will become change. Okay, got it. This is what happens. And this kernel is a mathematical function. That's what I told. Na? RBF is a mathematical function only. Na? That helps to organize data and make it easier to classify. Especially, see, this terminology is specially for classification only, kernel trick. However, in real world scenarios, the data is not linearly separable, obviously. Linearly separable is the easiest case. Kernels here may be implicitly mapping. We are mapping. Okay, this point is present in 2D, how it can be mapped in 3D. This point is present in 2D, how it can be mapped with 3D. How? So what is present in 2D, this is your input space. How this can be mapped into 3D, that is your feature space. That is why SVM is a heavy algorithm. It takes time to solve. In all the machine learning algorithm, SVM is complex. Why? Because it needs to do this task. It will transform the data, input space into the feature space. Okay, that's what it will do. Got it. And it take time. If you are having a data set, huge data set, then it will take time, obviously, to solve. Got it. So, why use kernel? Non-linear. It can handle the data. Any data points which are not linearly separable, use kernel. It will handle. It will tackle that thing. That can be achieved without explicitly performing the transformation. We are not explicitly performing the transformation. It is saying that which is computationally expensive. However, still we are having some complexity. SVM is not an easy algorithm. Still we are having the complexity, but we can manage. Here we are doing map. You know what happens? Mapping function is a mapping. So we are having kernel as a function. So we map a 2D point to 3D point, just to avoid this confusion of intermixing of the data points. Okay, got it. So flexible, depending upon the nature of the data, you can select your kernel. Feature extraction. Kernel can implicitly perform feature extraction by projecting data on the space. Okay, we can perform the feature extraction, and that's what we call as a kernel trick. Okay, so higher dimensional feature space, projecting the data from lower dimension to higher dimension. Okay, and the key idea is this only. No need to explicitly compute the mapping of higher dimension. Instead, kernel function compute the similarity between the data points. This kernel functions will help. Okay, if this point is present in 2D, how this point will look in 3D? That kernel function will do. It will coordinate. It will coordinate that if any point which is present in lower dimension, how this point will look when it would have been present in higher dimension. That kernel trick will perform. It will compute the similarity between the data points in the higher dimensional space. And SVM handle complexity, non-linear relationship. That's what we are saying, non-linear relationship between y and x. And this is how we can also told about the regression. Okay, so some of the commonly used kernel functions are linear, polynomial, Gaussian, sigmoid. These are famous, and these are the formulas. See, for linear, I don't have any issue. X dot x, like this. This is something. There is no issue. For polynomial, it can be power of d, something, some power. If I'm having two parameters, x1, x2, so linear will be y equal to mx1 plus x2, like something like that I can make. And this can be like put into the polynomial to the power d. Gaussian, this is exponential. Asymptote is 10h. whether it's 10h or you know about the sigmoid. What is the formula for sigmoid? 1 upon 1 plus e की power minus x. This is the formula for sigmoid. Okay, so x1 and x2 are the data points, and gamma. There is one more term, gamma. D is the degree of polynomial. Okay, we are having gamma here. So these are the data points. Okay, so mx plus. Okay, let it be whatever I have written. These are the data points. Okay, and D is the degree of polynomial here, of degree anything, 2, 3, whatever. C is regularization parameter, strength of regularization, strength of penalty, which you can enforce. Okay, and we have seen this C in regression also. Okay, like L1 and L2. We have seen in hyperplane this SVM also in terms of lambda, and now in terms of regression, it is C. In terms of regression, it is C. To control how much penalty you can apply over the constraint so that we should have a proper classification. Okay, got it. So gamma used in RBF, as the value of gamma increases, model gets overfit. As the decreases, model underfit. So we should have a proper value of gamma. We want to make a general model. Linear kernel. Okay, it's the simplest one. I don't think we have to discuss about. It's an advantages is simple and the fast. We have derived our formulas based upon linear only. Okay, because taking other cases are complex, the maths will be much more tough. So we have derived our formulas on the basis of linear only. Okay, so linear is not suitable for non-linear data. Obviously, linear is for linear. For non-linear relationship, we can't use it. Polynomial kernel allows more complex decision boundaries. The kernel can capture interaction between the certain degree. If the relationship between y and x is non-linear, okay, y and x is non-linear, then use polynomial kernel. Okay, it will help if you can't classify polynomial kernel. Okay, it is computationally expensive. Now the thing is, when the kernel comes into the picture, then it need to perform the mapping. So mapping, it can be expensive. Here is the formula for the Gaussian. Gaussian can handle complex and nonlinear relationship also. So by default, in SVM, we do have Gaussian only, RBF. If you just write like this, from SVM dot, okay, from SVM dot import support vector classifier, and if you use like SVC support vector classifier, so by default here RBF will be there as a kernel, not linear. RBF. For linear, you have to mention kernel equal to linear. That's what you have to mention here as an hyperparameter. So by default is RBF, real basis, because it can handle complex and non-linear relationship. We assume initially as non-linear relationship only. That's what our assumption is. Okay, got it. Linear is simple in nature. Okay, so that's the thing. All right. Sigmoid again use a model for relationships similar to those found in a neural network. If the distribution of data is something like which we have seen in the neural network, also in machine learning too, logistic regression is based upon sigmoid only. It depends upon the data, how it is distributed. So, how to choose a right kernel? Data complexity. For linearly separable, the linear kernel is sufficient. If we can see the distribution of data, we make plots. So we can make a plot between y and x, and we can see whether how the things are going. So accordingly we can use the kernel, decide the kernel. For computational resources, RBF and polynomial are expensive. That's why I told it takes a lot of time. It takes a lot of time for SVM to finish. If your data is huge, the SVM take time to map. Okay, 2D to 3D, like a lower dimension to higher dimension. 2D is just an 2D and 3D are just an example. I'm saying it will perform mapping of that point to higher dimension. So this will take time. Whether you are taking SVR, whether you are taking SVC, it will take time because it performs the mapping, and then only it will get solved. Okay. So whatever be the kernel we use, we need to perform. Okay, if your scores are getting less, whether you are doing classification, whether you are doing regression, if the scores are less, then you can change the kernels and identify which one is better. Still, if you are not able to understand how the data distribution is there, you can perform cross validation. Okay, so kernel project data from its original to higher. Remember, making possible to find linear separation. Linear separation. See, SVM in core, it's for classification. The deviation of SVM is towards classification only, but we can do the adjustment by considering this case as epsilon tube instead of hyperplane, then it will convert it into regression. Okay, in general, SVM is like more towards classification. The approach is like towards classification. Okay, so we do perform mapping here implicitly. Implicit mapping, not explicit mapping. You did not have to write specially anything else. Explicit means you have to code separately. Implicit means it is already inbuilt inside the code. It is already inbuilt inside the SVM algorithm. You did not have to write any code to perform the mapping of 2D to 3D. No, already present inside the SVM. Just use it. Okay, so the maths behind the SVM we have seen already. This is what we can write: sine sum of summation of alpha, then alpha I, yi, k xi plus b, something like that, where xi are the support vectors, yi are the class labels. You have already seen y wx plus b minus 1 greater than equal to 0. This is your constant equation. Yes, that's what they are writing. Just similarly, that's what they are writing. So yi are the class labels. Alpha is the Lagrange multiplier. Okay, so alpha you can take lambda, and kxix is a kernel function that computes the inner product. Inner product of the trans. See how you can project this point to this point. Product. There will be inner product. Okay, so you need to take the dot product of a data point with the function, with the kernel function. Something you have to do is a kernel function which computes the inner product of the transformed space. Okay, we are having Lagrange multiplier alpha. We have to find its values also under the constraint. We have seen that in the SVM entire derivation. Okay, so this is your linear kernel. That means x into x dash, x dash. That means inner product without transferring. There is no transference. It is effectively linearly separable. I want to transfer this point to this somewhere. With whom I will multiply? You have to multiply with the function. Okay, right now I'm multiplying with a linear function, so there will be no transformation as such. If you multiply a point with any high order function, okay, so that will be transformed according to that. So there will be product of this point with this function. Function will, okay, that's what they said. There will be inner product. This function will perform inner product in the transform space of your data points. We can have polynomial kernel to the power d. We can have a radial basis. Okay, this is what the formula for radial basis. We can have a sigmoid kernel also. Tan h of alpha x into x dash plus c. This is sigmoid kernel. So we are having this certain types of kernel, and how to choose this kernel I have already told you. So regularization parameter I have explained. Okay, and the equations which you have seen in the SVM, your classification regression. In classification you are having w square by 2 plus, you can take like y wx plus b minus 1 greater than okay, this is L equal to, let me rub this thing. Okay, let me put this as a minus sign. Okay, let me put it here as a, this is, okay, we have to multiply lambda, but I'm not doing here. This is your objective function and this is your constraint. And in case of regression, you are having again w square by 2 as an objective function, but the constraint is c summation of slack plus slack dash. Okay, this is the equation, constraint equation for regression. Okay, for SVR, you can check it. Here it is. This is constraint equation. Okay, and the rest is what you have to follow is trick, kernel trick. That's what you have to follow to solve, which is not linearly separable. And how, what it will do? It will map. It will map. Map is just like transformation only, but internal. Internal means implicit, means internally the function will do. How it will do? Multiplication. How? Inner product. How? What is inner product? Dot product of data points x dash something, like k is the kernel function. That's what they are taking. How this point will look in a high dimensional space? Just make a data point, do the dot product and show it. That's what the entire terminology of SVM says. Okay, fine. So that's what I need to explain in this particular lecture. Let me stop sharing.